constant. And we're going to turn our attention now to the man who has been the driving force behind ZeroAvia from the beginning, our founder and CEO, Val Miftakhov. I'm going to invite Val on stage for a conversation, and first we'll go through a fireside chat format. I'm going to ask some questions to Val, and then we'll put some questions from the floor to him also. So do please add as we go, and perhaps pick up some of the questions. We'll perhaps pick up some of the questions from the earlier panels as well that we didn't quite get to, because I think some of those Val will have a really interesting take on. So with that, let's bring Val onto the stage. Val, I'm not sure if you can turn your camera on. Hopefully we'll be able to see you shortly.
Should be on now.
We haven't got the camera. Let's just take a pause. The team setting issue, I'm not sure. You might need to hit, if you hit top right corner, you might need to hit the camera icon above the screen as opposed to the bringing on stage icon. Hopefully that will work. There we go, perfect. I hope you're joining us from a slightly sunnier spot. I'm here at Kemble, which has been 4 seasons in one day. Absolutely terrible weather this morning, but it's starting to brighten up a little bit now. Daya, so thanks for joining us. As I was kind of recapping before you joined, we've had a really good introductory session. Some reasons to be positive, some challenges facing the sector, but a real commitment from lots of players to the technical barriers we need to overcome and some of the ecosystem barriers as well. I'm just curious to start off with, this is our 6th annual Hydrogen Aviation Summit. It's an event that's been enormously successful year after year. I'm just wondering if you can give us your overall reflections on the journey to date, where ZeroAvia has come from, where the sector has come from, and also, where we are now, what you're seeing now in the market.
Of course, thank you, Dom, and of course, great to see and hear everybody who's joining us for the 6th time. And this event has become, of course, a staple of the hydrogen aviation, hydrogen electric aviation especially. And I know there are a lot of familiar faces and familiar voices in the audience as well. So great to have everybody together again, and taking a stock where we all are and how to move forward. So reflecting on the journey, it's definitely been an interesting one so far, as every pioneering journey, trying to bring the fundamentally new technology, new approach to the field. We're, of course, as Dom, you mentioned, we've been through several twists and turns, but I think we're all, and I'm not just talking about the company, but also about the hydrogen industry, hydrogen electric aviation, and aviation overall. We're fortunate to be able to continue on the journey that I firmly believe is the right solution for aviation. As fundamentals of hydrogen, fundamentals of electric propulsion still stay the same. And it's still the most efficient way to power larger and larger aircraft with this kind of fuel. And in fact, while all the market tribulations are happening, we've been making steady progress on the technology side. And that made us even more convinced with new applications opening and with new technology being developed in the high temperature fuel cells, in the liquid hydrogen space, in the overall system development, that this is the right solution. And there are a set of people, you mentioned Airbus, of course, with the hydrogen electric announcements, a number of investors that are firmly with us in the space. And I believe that we will definitely get there very, very soon.
And you, Val, as a physicist, a scientist, you like to go back to first principles, and this is the 6th edition of this session. But I think many people will be joining us for the first time. I'd like to dig into 2 things. One is if you go back those 6-7 years ago when you first started approaching the problem, you say hydrogen remains a key part of the solution, it's a big part of the solution. What kind of led you to that conclusion then? And then let's maybe touch on what some of the big developments that have increased that belief.
Yeah, of course. Even over 8 years now, and actually I was thinking about it even before starting the company. To start in the end of 2017, and at that time there were a lot of electric drone projects already, or rather UAS, UAV, and some of the VTOL projects were starting out. And I'm coming before ZeroAvia started and developed and then sold the company in the electric vehicle charging space. So it was really involved in a lot of the electric mobility already on the ground, but still we built the world's largest network of smart charging stations for it. So knew a bit or two about how to bring electrification to the markets, and spent a lot of time with batteries. And it was clear to me that while batteries are great for ground mobility, it will be very, very difficult to make them work as the primary propulsion energy source for aviation, especially for commercial aviation. Maybe small aircraft, maybe short distance, okay, but a large aircraft, long distance, turnaround times, and being in the operation for 12, 14 hours a day is very, very difficult. And I'm, as you mentioned, a physicist myself. I looked at the physics and chemistry of it, and it just did not make sense. And everybody at the same time was running around and saying that batteries are going to become 10 times better in the next 5 years, and we're not going to need anything else. And of course, that did not happen. But we saw it from the beginning, and at the same time, electrification is the next step, and it is much cleaner. It's much more efficient way to do things, and cleaner doesn't just mean CO2, climate change. It also means particulate emissions near the airports. It means a lot of things. So really, it is the better product, electrified. But you need energy. And the way to get energy, we thought, and we see that playing out better and better now, is through hydrogen and hydrogen fuel cells. So since then, we've made a lot of progress, 3 generation of flying prototypes, and now moving to the certification of our engine. We're about halfway through. Certification projects in the US, in the UK. We've got the certification basis approved, special conditions approved in the US, got design organization approval in the UK. So really making outstanding progress towards actually making it commercial.
You mentioned the various flight tests that ZeroAvia has undertaken, and what's particularly interesting, and we'll come to this in a little bit more detail about you and your passion for aviation, but you are a pilot yourself, and one of the questions we often get is it any different to fly an electric aircraft? And I'm just referencing the fact that you previously flew an early demonstrator. So could you give people who are pilots who might be interested in that, maybe people who've driven a combustion car, an electric car, what's it like to fly an electric aircraft?
Yeah, absolutely. And I'll take this analogy further. So I guess that's a pattern for me. So in my previous company, Electric Motor Works, where we built the charging stations, I actually started the company with converting a few cars to electric propulsion. And so I was driving those cars every day for a number of years before setting up that large charging network and working with energy companies and all that. And in the car space, or as a driver, the electric car is a better car. Some people like the noise, but I don't particularly like loud noise in my vehicles. So that was a perfect situation for me. And then that also translates to electric aircraft. And for those of the audience that have been in electric aircraft, you can also attest to that. Especially in a smaller aircraft, the noise levels are much, much lower. The throttle response is much, much better. and generally the system feels more responsive. My sort of pilot experiences across the fixed wing and rotorcraft, so noise reduction is quite substantial. Then there are second order noise reductions as well. So first one, of course, your engine does not produce any noise. But then once the engine does not produce any noise, you have a lot of opportunities to reduce noise further from the propulsors as well. Whether it's main rotors or tail rotors in a helicopter, or main propeller and propeller airplane, you can now take advantage of the electric motor power and torque band capabilities, and let's say deliver the same amount of power but reduce the rotational speed of the propulsor, and that reduces noise dramatically. So those are some of the and we tried it at ZeroAvia, of course, as we were flying prototypes in our smaller vehicles. We actually shown this successful operation, and now you also see a lot of the data from the leading VTOL companies, leading electric aviation companies like Joby and others on the noise reduction that is possible with electrified propulsion. But again, you need energy, and that's where the hydrogen fuel cells come in.
Fantastic. So, and what we've covered there off is a little bit of the experience as a pilot and how the systems are different. You and the team, you've been at this now for 7+ years, 7-8 years. What are you seeing now as the key technical challenges to getting systems through to certification? That's obviously the big goal. What are the big barriers to overcome? And how will hydrogen systems change the future shape of aircraft?
Yeah, of course, the key challenge right now is we're in the middle of the certification program, as actually getting through the certification program. And a lot of those are, in fact, around the fact that there is no supply chain really for this new aviation engine approach. Yeah, when you talk about compressors for the fuel cells, there are no aviation-grade fuel cell compressors out there. You look at the simple things like sensors and valves and connective apparatus for various gas and fluids. You don't have certified hydrogen components out there, or at least not a lot. And as a result, we have to push the partner network supply chain to actually walk that journey with us. And in some cases, when it is proving to be too slow or too difficult for the partners, we have to do it ourselves. And I think a lot of the pioneers in various industries have similar approach. So you look at Tesla, for example, that had to verticalize a lot of the systems and production inside in order to push progress faster. So we see a lot of those challenges, which is interesting now that we got the technology working and proven through this multiple generations of prototypes and flying prototypes. Now the challenges are sort of in the middle between the technology and production and certification, if you will.
Yeah, absolutely. So we had a fascinating set of panels already, as I mentioned earlier. We've already covered kind of UK and EU status quo and the plans to push through to adoption. Our next panel is about the future aircraft development fit for hydrogen. What have you really learned from talking to the OEMs about how you develop a propulsion system that's completely new? It's a new age of electric aviation. Yeah, what have you learned from the OEMs on this journey so far?
Yeah, so we have partnerships with give or take 8 aircraft manufacturers, all the way from Textron to, of course, Airbus as one of our lead investors in the company. And many of them are quite involved in our development process. And specifically, as our first launch aircraft for full engine, our 600 kilowatts engine system is Cessna Caravan. We spent a good amount of time with the Textron team looking at various integration aspects. And some of the learnings included on that aircraft specifically how to get the fuel system properly together, integrated with aircraft, how to look at the various structural components and ensure the safety of aircraft with these new type of not just propulsion but also fuel. So we're approaching gaseous fuel as main storage for that aircraft, and you see it on your screen in the corner there in the pods under the aircraft. These compressed cylinders are very rigid objects. So how do you make sure that the cabin is not penetrated when you have a hard landing and things like that? So a lot of the
effectively point to the exact spot. There we go. Just
exactly. Yeah, a lot of the standard structural issues, but new with this new new fuel and new types of tanks, because you don't see those types of issues with the conventional fuel. And then on the propulsive side itself, because this is new technology, the experience is virtually non-existent, and in aviation as electric as a primary propulsor. So as a result, the regulators are hesitant to give pretty much any credit for the reliability of the fuel cells and some of the other components. So we have to design the system with such level of redundancy that those questions become irrelevant, basically. Yeah. So our engine is designed as triple or quad redundant, with failure of any of the 3 or 4 channels not affecting the overall performance of the aircraft, or at least allowing us to still climb and fly away. So as a result.
Yeah. So yeah, so the knock-on impact there would be that with that additional redundancy, you're building more into the system, you're adding more weight. So in theory, as more flight hours are accrued, more safety data is accrued, you then potentially move to a system where a place where the systems actually operate even more efficiently. Is that a fair assessment?
Correct.
Okay, so carry on with where you were going with the next point.
So it is a more safe system as a result. So typical single-engine aircraft, if you have any problems with the engine, then it quickly becomes a glider. So in this case, when you have effectively 3 or 4 engines in one, and the only place where the power sort of connects in a single place, a single point of failure, is the propeller shaft and a propeller. This is a much safer system. So those learnings, of course, are also not lost on the operators, and that's why over the last years we were able to get over 3,000 orders for our engines, and significant also interest from some additional markets outside of civil aerospace. Defense has been quite a big hit for a number of reasons. I'm sure we'll get into it as well.
Yeah, absolutely. So we'll come to the defense topic in a little bit shortly. One of the things is thinking about hydrogen and thinking outside of hydrogen. When you think forward to 2050, which is a slightly daunting thing, so it's a quarter of a century away, but when you think forward to 2050, how do you envisage the future of our skies? What will it look like for the average person? What's the opportunity to fly? What will be the typical modalities? You mentioned AAM and eVTOL. How are we going to see the skies change over the course of the next 25 years, and what role does hydrogen have to play there?
Yeah, I believe pretty much all of the regional aviation, and I define it as let's say 100, 150 seat aircraft or smaller, going under 1,000 miles. All of that, I think, will move to electrified propulsion, and vast majority of it, in terms of the seat kilometer flight metrics, will be hydrogen electric, because that's just a way to get better economics and better performance characteristics out of the aircraft, and it will be a combination of sort of smaller VTOL type players that will provide services for the connectivity. to the main hubs, to the main airports. So kind of like what we have today, but going even further down in the spectrum of locations. Yeah, today we have regional aircraft providing connectivity to a lot of the hubs from which international flight or long distance flight occurs. But still, that connectivity by regional aircraft even is provided from the limited number of airports, smaller airports. So now with VTOL proliferation, that I think will happen, we are going to see a lot more locations connected and perhaps shifted from ground-based mobility connectivity. All of that drives more and more traffic into aviation. And that makes it even more important to make sure that our expansion of aviation is electrified to as much of an extent as possible. And again, we firmly believe that the way to that expansion is through hydrogen as a carrier of energy.
Super. And again, so returning to defence, our last panel today is a superb panel. We've got retired Air Force General Mike Minahan joining us for a defence-focused panel at 7 p.m. You know, what are the, just turning our attention to that, but a lot of people might be familiar, might be more in the commercial sector. What are the key use cases and advantages for hydrogen in that defence context, and fuel cells as well?
Yeah, this was an interesting journey for us, as especially over the last I would say 18 months, as we rolled out our component strategy. About 2 years ago, we said, hey, there's a lot of demand out there, not just for full engines, of which, again, as I mentioned, we sold about 3,000 of those on a pre-order basis when they become certified and available. But a lot of people were coming in and saying, well, the engines are great, but we have this aircraft and we already have distributed propulsion system that we've developed, but we need a better energy source. We wanted to go for batteries, but hydrogen electric sounds better. So we developed this product set, the component set for players like this, and that's when we started seeing defense as a strong interest customer. And fast forward now, we have 6 or 7, depending how you count, projects in defense. 4 in the US, 1 in the EU, 1 in UK, and one additional is coming up. The advantages there arguably could be even stronger than in civil aerospace. So main advantages are, of course, we talked about the noise. So noise signature is much lower, and you can make it much lower with electric propulsion, but you need energy for the mission capability. Then your heat signature, which is not really important in civilian aviation, is quite important in defense for detectability of aircraft. And of course, with hydrogen fuel cells, you don't burn anything. So there is no high temperature exhaust. There are no high temperature parts on the aircraft. So detectability is much lower, which is great for surveillance missions, especially. Then because we have electric propulsion and large source of electricity on board, powering all the payloads, again, surveillance aircraft, radars, and other electronic equipment, surprisingly, a lot of power is being consumed. Sometimes in sort of small and medium type vehicles, half of the propulsive power can go, or equivalent of half of the propulsive power can go to that equipment, which presents huge challenges for combustion engine operation, where you have to put large generators on top of the turbine and extract that power out, which adds weight. So with a natively electric propulsion, you get that electricity for free. Once you climb up to the station, you can provide a lot of that power. And perhaps lastly, but not least, is fuel availability. So fossil fuel or traditional liquid fuel requires a lot of logistics, especially to get to forward bases, remote operations. With electric battery, of course, but also hydrogen, you can generate your fuel on site, say with renewable power, solar panels and whatnot, and electrolyzers. Again, you can do this for the battery aircraft, but you don't get the range and payload. So lots of advantages. Perhaps half of those are unique to defense, and that's what drives a lot of interest.
Yeah, and some overlap there also in terms of the advantage with commercial. So we've talked a lot about energy sources. All of the benefits of electrification. One of the key challenges is energy sources. It's a question that's come up in quite a number of questions from our audience. So I'm just going to draw our attention there for a minute. So one question here is from Keshav Chowdhury, and Keshav asks, as the battery energy densities keep increasing year on year, how do you have the conviction that batteries will never get through to have enough energy density to make them viable for short and medium haul aviation?
Yeah, so of course they're increasing, but if you take a stock of almost 10 years ago when we started the company, at that time the batteries there was no battery project really on the certification path to aviation. Now we do have, so maybe comparison is a little bit of green apples to red apples, but apples nonetheless. The energy density of the batteries was around 200 watt hours per kilogram. Today, the best certification path batteries are between 250 270 perhaps watt hours per kilo. So that's a 30% increase over the course of 8 years. With that kind of pace, we're not getting anywhere near the energy storage capacity of something like hydrogen. And but as Dom mentioned, as you mentioned, we looked at the first principles, because you don't want to be, as an innovator, you don't want to just look at, okay, well, this is what we've done in the past and let's project it forward. We actually looked at, okay, if you take the practical constraints out of the battery, what are the maximum energy densities that you can achieve, and how would that compare with what you can get from hydrogen? So the best type of battery that we have today is lithium based battery. So lithium atoms or ions carry the charge from one side to the other, and that's how you produce the current. And if you just take lithium atoms and their weight and a ratio of charge to the weight, you get energy density, maximum absolutely possible energy density from lithium-based carriers that is significantly lower than hydrogen already. But then you need to carry those ions in some kind of medium, so that's electrolyte, whether it's solid state or otherwise. And then you need to store those ions on both sides of the battery as they move from one side to the other. So that adds additional constraints. And you have to have those cathode and anode materials. And even before you talk about the practicability of releasing and storing that amount of material from one side to another, you have theoretical constraints on it. So once you take all those into account, theoretically, you have at least 10x gap between the hydrogen as an energy carrier and best possible lithium-based battery. And we haven't, as humanity, we haven't figured out yet what could be better in terms of storing a unit of charge per unit of mass atomically than lithium. Now, completely new types of batteries could be invented at some point in the future. But they're not here today. And hydrogen is here today. Fuel cells are here today, and they can provide orders of magnitude better relative energy storage capacity.
Superb. Great. That's a very clear explanation and taking us back to some of those principles. I want to also cycle back now to the defence case, because we've got a great question from Charlotte. She asks, which dual-use defence applications help realistically speed up certification times? And have you always considered this market from the start?
We have not considered this market from the start. Definitely not 7 or 8 years ago. this realization of this market applicability happened, I would say, maybe between 2 and 3 years ago. Again, as we started pushing into the components, especially because all of these vehicles are pretty different, typically from the civil aerospace type vehicles. So we're working with a lot of the unmanned vehicle space in the sort of medium, large size unmanned vehicles, and those are designed differently. Obviously, no pilots, very different systems installed, and all of those things. So this was a unique application there. Now, from the airworthiness perspective, people are looking for the same thing. You have to have reliability, and you have to have a way to design, way to build these things that can pass airworthiness constraints applied by departments of defense out there that are, in a lot of cases, derived from the civil aviation authorities' experience. So definitely helpful. In one or two of these examples of the real life projects that we have, we see a lot of similarities, and that's pushed our designs to a better place where we're able to leverage it into the civil space as well. Sort of similar to my earlier answer to one of your questions, that also helped us push a good bit of supply chain to meet those requirements as well, which will be quite useful for us in the certification for civil use.
Terrific. And we've got a few more questions coming in of a technical nature, which I'm going to return to. We're just going to take it in a slightly different direction and ask a little bit more about you yourself and some of your personal motivations. And perhaps as a way to kind of straddle these two of thoughts on the technology in the market and ZeroAvia, I kind of wanted to ask, when you, what's keeping you up at night?
Well, I think the timeline to certification and underlying question there is how conservative the regulatory community will eventually be around these technologies. There is a way to be too conservative on these things, and ask for too much. Understandably, this is new technology, and more scrutiny needs to be applied. But also, there is a lot of experience, both in the at ZeroAvia, but some others, but also in the ground mobility around fuel cells, around say electric propulsion, that I'm hoping we will be able to bring to a force here, and accelerate the certification progress and get this into the market as quickly as possible. Initially, our approach is to go to small aircraft, Part 23 aircraft, where the risk levels are lower, the certification hurdles are lower, so that we can get this product, this technology, to commercial operation as quickly as possible. And we think that demystifies it quite a bit, both for regulators, but also for the operators, for the OEMs. So time to that initial commercial product introduction is the most important thing right now.
Super, and this all speaks to the fact that one of your big drivers is your passion for aviation. So could you describe to us where that began? Where did that passion for aviation come from, and why is changing it a particular passion?
Yeah, well, how far back you want to dig is a question. So I grew up in Soviet Union, and my father was an avionics engineer back in the day, and we had a lot of aircraft aviation discussions and visits to various airfields and museums and similar things in my childhood. So maybe that's where it all comes from. So when I immigrated to the U.S., was about 30 years ago, one of the first things I did, I enrolled into the pilot school here, because in Soviet Union you couldn't really, outside of the military, you couldn't fly anything. So here in the United States, in California, that's what I did. I got my first primary license as a helicopter pilot, which is, as I was told by many, the wrong way to do it, because it's more expensive and it's harder. But nonetheless, that's what I did, and then flew around quite a bit in California, and realized that helicopters are nice and very versatile, but A to B, maybe not as great as a transportation, and that's when I got my fixed wing license as well. So I got well over 1,000 hours of flight experience at this point across various platforms. Really passionate about aviation, as you can tell, and right about maybe 10 years ago, started seeing, especially as I connected to this new mobility space, electrified mobility, clean mobility, as part of my previous company, started seeing aviation challenge in sustainability. And then digging into it, also realized that getting to electrified propulsion also makes it efficient, less noisy, and really, as I mentioned before, better product. Just like in electric cars, the electric vehicle is a better product. It accelerates faster, it has lower noise, obviously it doesn't smell gasoline, you don't have to go to the gas stations, to the petrol stations, and do all of that. In aviation, you have a lot of similar advantages, and this will really make electric aircraft a better product. And of course, you have all the sustainability benefits, but it will be a better product. So I felt that, especially after having been exposed to the electric vehicle revolution on the ground, I wanted to accelerate the push in aviation towards a similar objective, and that's why we started ZeroAvia, and that's why we continue doing what we do.
So and you've obviously been on a journey both with eMotorworks and ZeroAvia. I'm curious as to thinking back on your time, what's the one piece of advice you've either given yourself when you started, or you would give to a young budding entrepreneur now, as they start to think about trying to bring a product to market, perhaps even in a deep tech sector, or perhaps even in aviation?
Yeah, great question. And I would say constantly be in tune to the market conditions and outside world, be ready to pivot. So this defense applications is a good example of how we are doing it in real time or near real time. At the same time, of course, have continued conviction in your first principles based approach. First principles is important because otherwise you don't have a strong value system, if you will, to stand upon. And changing market conditions, changing environments out there can make you rudderless if you don't have first principles conviction behind your technology, behind your product, behind your approach. So a combination of the two is very important. You have to have first principles guiding your main direction, but on the way there, be ready to take twists and turns and pivots based on what learnings you extract from your journey.
Super, that's very helpful, I hope, for some of the audience. And going to return now to some of the technical questions. Particularly, we've talked a fair bit publicly about the fact that to scale for larger aircraft, there's the next generation of technology, which might involve higher temperatures of fuel cells, and we've also talked about the criticality of liquid hydrogen. So I'm going to take these one by one. Question here asking, back in April 2025, in an interview with David Roberts on the Volts podcast, you mentioned that one of the big challenges in fuel cells is achieving these higher temperatures and developing these high temperature PEM. Can you maybe unpack how that works, why that makes a difference to the performance of the fuel cell systems, and give an update as to how that technology is evolving?
Yeah, so we have in-house development of high temperature fuel cell systems, of course, and it's going well. We're making significant progress performance-wise. We have achieved the levels of performance that we're looking for already at this point on our roadmap, and we're shifting our focus on durability and time to overhaul, if you will, speaking aviation language for those things, which is great. New set of challenges, but great to see that the performance side of the equation is really achievable at the targets that we've set ourselves. The overall advantage why we're doing it for the high temperature fuel cells, of course, is the high temperature now that's still nowhere near the combustion temperatures. Yeah, so all of those benefits that I talked about on the detectability for defense or NOx particle production or lack thereof in the fuel cells are still there. So we're talking about, instead of 100 degree Celsius operating at just under 200 degrees or around that temperature for our fuel cells. So still quite low, meaning that material stresses do not become an issue still. You can still run aluminum, for example, as some of the structural components of the fuel cell, which allow you to reduce the weight quite a bit, things like that. But the main advantage, even in that moderate temperature increase, is that the temperature difference between the fuel cell core, operating core, and the ambient temperature becomes much, much greater, which means that cooling that system is much, much easier. These become very, very important in the hot and humid situations, for example, and we have to certify our systems to, let's say, 50 degree Celsius operation somewhere in Dubai, for example. When you have the low temperature fuel cell operating at just under 100 or around 100 C, the temperature difference is just 50. When you operate the fuel cell at 200 core temperature, the temperature difference is 150, so 3 times. And that makes cooling much, much easier, and that drives the weight down, and the system can become simpler. So really great advantages there, and the further you go on the size of the aircraft and the total power density, the more advantage you have.
Super. And then the question I'm referring to on the liquid hydrogen, great question from Stefan Andres from Piasecki, our friends there. Stefan asks, I recall that you're also looking at liquid hydrogen tanks. Can you give us an update on the progress of the liquid hydrogen tanks?
Yeah, absolutely. So we have several actually programs on this. One of those programs is in-house program. We've made quite a bit of progress on that. We have a project on a composite tank with an external partner, done some tests up to 30% mass fraction or similar. Composite, of course, is a little bit more complicated in cryogenic settings, especially when you talk about the certification. Regulators are quite cautious around that because the properties of material, especially composite material, can be problematic with the cryocycling. So that's why in-house program that we have is around the metallic tanks, aluminum-based, and there we already achieving over 20% mass fractions on those tanks with all the integrated components that you would need for aviation use, including vaporizers, including structural components to withstand crash loads for certification. We have and grateful for great support from ATI Aerospace Technology Institute on development of some of those technologies as well, and we're hoping to get them to flight relatively soon. Definitely getting to demonstrable hardware within probably the next 12 months on these things, and this will be relative to what's available right now in various development efforts on the market. This will be quite a bit of improvement.
Super. We have another question here from Nicholas Barrow. So how do you ensure that the introduction of clean sheet hydrogen electric aircraft can coincide with conventional fleet replacement schedules? So clearly there's a lot of concern that these new technologies in development, but a whole new raft of aircraft will be delivered in the meantime with a 30+ year life cycle. So, how are these things going to be coordinated and work in step?
Yeah, really, well, the best way to ensure it is to get this product out there, get this technology out there, and start getting the level of confidence from the markets that this is really not just achieving its technological objectives, but also operational objectives, which means availability of fuel, economics of flights, turnaround times, and dispatchability numbers, which we think we can actually deliver better than conventional fuels aviation, especially in the smaller aircraft. But we need to show it, and people need to see it in order to accelerate the adoption. The best way we think for us is to continue that work with these 8 different key manufacturers, OEMs, in the aviation space, to make sure that they're involved in the technology development, they're involved in the integration work for their aircraft at the early stages, so that our partners are familiar with the technology and can start working on the clean sheet designs as soon as practical. And in some of those cases, we're already working with the OEMs on the clean sheet designs of the vehicles.
Okay, and we've got a question now that's going to take us right back into the fuel cell systems. And you talked a little bit about those super hot days, 50 degrees C. This time we're looking at can you address the cold start of fuel cells? Perhaps Karim, who's posed this question, is aware of the fact we have a plan to launch 15 Cessna Caravans in the future in Norway. Obviously, we've got partnerships in Canada, these super cold regions. What's the cold start scenario for fuel cell systems?
Yeah, of course. Yes, this was a great win for not just us at ZeroAvia, but also I think the whole aviation industry to get that support from European Union on this launch in Norway. This is the first such project, I would say, that will pioneer the use of hydrogen electric propulsion in a real commercial setting at a real scale. So really excited about that. The answer to the technical question there is, in the automotive space, of course, that problem has been solved a long time ago, and actually that problem is much easier than battery electric propulsion in the same type of environments. Where what you need to do is you need to just heat up the fuel cell active material to the operating temperatures or above zero or above freezing. And then the system can be properly started up as it normally does. The thermal mass of the active material in the fuel cell is relatively small, much smaller than the battery thermal mass that you would have to activate and heat up in order to have proper operation. So from that perspective, hydrogen electric again wins on the sort of spectrum of electrification technologies, how quickly that can be done. Literally in minutes, this can be heated up to the operating temperature and then started up conventionally. So that's the approach, and again, it has been done in automotive. All these cars are operating fuel cell cars, and other vehicles are operating in harsh environments all over the world.
Yeah, and returning to the high temperature setup, and I suppose more generally, and we have a good panel addressing this tomorrow with some of our fuel cell teams, some experts from some competitors, and also from some of the suppliers. So do tune in for that tomorrow. But when we're thinking about fuel cell systems and the development pathway, the high temperature fuel cells in particular, what are the other sectors that these advances in aerospace can then serve? Is it, or are they overspec'd? What's the potential spillover benefits there? That was a question that came up in an earlier session.
Yeah, very good question. We think it's really going to be across the board. Yeah, the advantages are fundamental, and that advantage of the thermal management or cooling is a universal advantage, and every application it will have benefits. Now in aviation, it will have strongest benefits because weight is so important and drag is so important. So any advantage you can take on the heat exchange and cooling of your engines is dramatic. Yeah, but it's still present in all the ground and marine applications, even in stationary power applications. So, for example, with the higher core temperature, and that's our approach, you can drive air cooling as opposed to liquid cooling of your fuel cells, which simplifies the system. So you don't have to have the liquid cooling path, pumps that fail, and multiple heat exchangers effectively, right? So you have to first take the heat out of the fuel cell into the liquid, and then from the liquids to the atmosphere. Here you can go directly, and your temperature differential allows you to do that, right? So that advantage crosses over all the different applications. So we think, once we get it working in aviation with a proper power density and durability, the applications will be plenty.
Super. So we've taken nearly the full hour, which is great. I think we've had some really good questions from the audience. Hopefully, people have enjoyed hearing about your journey, your story, your thought process, and also, a little bit more of a deep dive into some of the technological issues. I want to end now, if that's all right, with just some quick fire questions. So try and think on the spot.
Sure, fire at.
So, who is your hero?
Well, fittingly, I guess Lindbergh comes to mind. The long distance crossing, and this is something that I think we should aspire to do before too long on this hydrogen electric propulsion, and hydrogen allows us to do it. So we should go for it. Hopefully soon.
Superb. Your favorite aircraft?
Aircraft. Let's see. SR-71 comes to mind. So the fastest aircraft in the world so far. Hopefully, we'll see the new version of it pretty soon. My son is actually pretty excited about that as well. So this is his favorite aircraft on the simulator. And recently we went to one of the museums that still have some of them. So that's a great aircraft. Amazing that this type of technology was done, almost 50 years ago, right? And hopefully we'll see this level of innovation again.
And I'm going to close now. So I've got here the final question. Favorite place on the planet? And I've noted to myself, Kemble, Gloucestershire is allowed as an answer. Others that spring.
Cotswolds are pretty awesome. Yeah, and when we were picking the next place after Cranfield, that was a strong factor.
Fantastic, and also we plan our manufacturing facility in Glasgow, also a great part of the UK, and California and Everett, not too bad places to be either. So thanks to Val, been a really great conversation. We're going to be welcoming the next panel shortly, but any other questions for Val, throw them into the chat. If anyone wants to share their own feelings on their favorite aircraft that maybe compete with Val's, that would be great. But thanks again, Val. We'll move on now to our next panel.